Okay, let's get started. We're moving now to chapter 10, so we're jumping over chapters 8 and 9, which we'll probably get to. We'll get to chapter 9 next lecture, and then chapter 8 we'll probably talk about in Thermo too. So this is the same book. If you're planning to continue on, don't sell it back at the end of the semester because buying it again is pointless. Homework is due today, so if you haven't turned that in already, please turn it in. And then our next homework assignment is due next Thursday, so 1 week on that. And you notice that a lot of these are concept questions. In Chapter 9, it's all concept questions. So really for Chapter 9, what we're trying to understand is the background behind the diesel and the Otto cycle as we get to that. But in Chapter 10, we are going to do some problems that involve a significant amount of work. So there's only 2 problems that you have to actually work out, number 5 and number 22, but they are pretty big problems in and of themselves. They have multiple steps. However, we're doing examples today that hopefully should clarify it for you. Again, it's a lot of the same stuff we've already been doing as far as analyzing a steady flow engineering device, looking up properties in tables, and then applying those concepts to solving the problem. It's just combining it all together. So we'll work on that today and do several examples. As you know, final exams are coming up. So our class meets on Tuesday, Thursday at 9:30, which means our exam is Tuesday, May 2nd from 8 a.m. until 10 a.m. I teach another section of this class where the exam is Thursday, May 4th. You can come to either exam, but you have to let me know in advance. You can't wait till exam day and say, never mind, I'm going to go to the other one. If you're planning on coming on Thursday, you have to let me know before our exam on Tuesday. Don't just not show up and then try to show up on Thursday. Because if you just don't show up, I'll assume that you don't want to take the final and I'll give you a 0. And you need to arrange it in advance. What's that? Get it over with. That's the incentive. Have the rest of your day to enjoy. Get it over with. When I was an undergrad, the university I went to had a testing center, and for a lot of the exams, you go into the testing center to take it for the final, and you could do it whenever you wanted. And I took all of mine one after the other on the first day of finals just to get it over with, so I can enjoy the rest of the week. And that worked out pretty well for me. So, do as you will. So again, if you want to do the Thursday exam, you have to let me know in advance. So that's fine if you do. The seating's going to be tighter in that class, but you have to let me know. Additionally, please check Banner. Make sure that all of your grades are inputted correctly. So homework scores, exam scores, quiz scores, and if Banner. Blackboard. Okay, it was Banner before. It's changed a couple of different times since I've taught here. Blackboard. So check your scores, check your grades, make sure everything's inputted correctly so that if there are any discrepancies that we can correct them before I submit grades, because after that fact it's really hard to change anything. So just make sure you do that in advance. Okay. Any questions on that, on the final? We'll talk about the final, not this or the next class period, but the following class period. Our last day of class, a week from today, is a review period. And so we'll go through the whole semester, talk about what to expect on the exam, and hopefully get you better prepared for it so that you can come on Tuesday. So those of you who came in late, this is our exam time. Tuesday, May 2nd at 8 a.m. And then the other section meets on Thursday. Again, if you want to do the Thursday exam, you have to let me know in advance. So, okay. So today we're talking about vapor power cycles. So this all comes from Chapter 10. We're not doing all of Chapter 10. We're just talking about the first 4 sections of it because it's the one that is the most commonly used in engineering design. And then when we approach the second semester of thermodynamics, this is pretty much all we do the whole semester is power cycles. And it's really fun and interesting, and I love it. It's the meat of it. It uses everything that we've learned thus far and combines it all together. So vapor power cycles are a cycle in which the working fluid alternates between a liquid and a vapor. And generally, steam or water is the most commonly used working fluid in these power cycles. what we're talking about physically is usually a power plant. Okay, so a power plant has water as the working fluid, one, because it's easily available in very large quantities, it's inexpensive to use. The properties of water allow it to operate under the conditions which we'd like to expose it to, which is very high temperatures, and then being able to condense it back to a liquid without having to subcool it to a very low temperature. So water's a favorable working fluid for those situations, and they're used to generate electricity. So we have seen examples in our area of coal-fired power plants. However, nuclear power plants also use a vapor power cycle to generate the energy rather than using the coal to heat the water. They're using nuclear power. And then natural gas operated power plants, again, generally using water as the working fluid. So regardless of the heat source, meaning whatever we use in the boiler to increase the temperature of our working fluid above the saturation point or to vaporize it, regardless of the working fluid, the system is analyzed in the same way. So the process can be analyzed simply knowing the amount of heat that's added. Okay, we don't need to know if it's a coal-fired or natural gas or a nuclear power plant. We just need to know how much heat is added, okay, in order to analyze the cycle. Now, for cost purposes, we may want to know, or environmental considerations, we may want to know what type of a power plant it is. But for the thermodynamic analysis, it doesn't really matter as much. The Carnot cycle we talked about in Chapter 6, and it's the most efficient cycle operating between two thermal reservoirs. So we want to look at it and see, is it suitable for our purposes in a steam power plant as a vapor power cycle? So we're going to look at it under two different conditions. One, where it's operating completely within the dome, meaning that everything is saturated liquid vapor mixture in all states except for state 1 and 2, where it's state 1 is all liquid, state 2 is all vapor. So looking at it under the dome, state 1 to 2 is a constant temperature process, and it's isothermal heat transfer. So we're going from a saturated liquid to a saturated vapor. State 2 to 3 will be an isentropic expansion, meaning the entropy is constant. It's an idealized cycle, so we're saying that it's reversible and adiabatic from 2 to 3. 3 to 4 is isothermal heat transfer again. This time we're removing heat and condensing it. If you notice, however, at state 3 we're a liquid vapor mixture. State 4 we're still a liquid vapor mixture. And then from 4 to 1 it's isentropic compression, where we compress the fluid. It continues to, as the pressure increases, it will condense because the temperature is moving up the dome. It seems counterintuitive, but just by the position which we are operating and compressing a fluid, we're able to increase the pressure enough that it's condensing because it's not vaporizing. So we lower the boiling point, essentially. Okay, so that's one option. There's some negatives to it. Okay, so we can approximate isothermal heat transfer. This is done pretty easily in boilers and condensers because it's a constant temperature process during phase change that state 1 to 2 and 3 to 4 can be achieved pretty easily in practice. However, if we perform isentropic expansion from state 2 to 3, we're starting as a saturated vapor and we're ending up as a mixture, saturated liquid vapor mixture. So that low quality at state 3 results in problems within our turbine. Generally, we want steam going into the turbine and something very close to steam coming out, because if there's enough liquid within the turbine, it causes impingement on the blades, which can knock them out of balance. It can cause cavitation. There are a lot of other problems that occur when there's too much liquid in the what's expelled from your turbine. So it's not really great. From 4 to 1, isentropic compression involves compression of a liquid vapor mixture. We've talked previously about compressors are good for compressing vapors, and pumps are good for compressing liquids. Well, this is in between. So a pump isn't really going to work very well. A compressor is not really going to work very well. So it's pretty impractical to try to compress a saturated liquid vapor mixture. So we need to rethink this. Okay, so the Carnot vapor cycle doesn't work under the dome. Let's see what happens if we instead shift it up and move it above the dome. Okay, well immediately you probably recognize that there's a problem because what are we encircling there? Or ensquaring, since it's not a circle. Is that a word? Ensquaring. What's that? Huh? Okay, what's at the peak of the dome? Do you remember? That very tip of the dome, certain point, critical point, right? And what have we said about the critical point? Yeah, stuff's going weird there, so we kind of want to avoid it. All right, so we're operating around the critical point. That should be the first given that this is not going to be a positive. So the water in the turbine is no longer an issue, but compressing it to significantly higher pressure is a little bit more difficult. And then isothermal heat transfer in a single phase, so above the dome from state 1 to 2, is pretty difficult to control, especially if we're above the critical point. Okay, so it's not really going to work if we move it up above the dome. The only state that works kind of well is from state 3 to 4. Yeah, we can condense from a saturated vapor to a liquid pretty easily, although it's still happening at a fairly high pressure. So the Carnot cycle is not really a good candidate for this vapor power cycle. What we want to do is modify the Carnot cycle to take the best pieces of it and allow us to use it in a way which will be more suitable for our working fluid and for the operation that we want to achieve. So if we're trying to have a network output from this cycle, then let's look at possibilities for achieving that by just modifying it slightly. Okay, so what we can do now is we superheat the steam in the boiler and then condense it completely. So the Carnot cycle before, if you remember, at this junction with the saturated vapor line, it would have just been an isentropic compression completely done. Okay, well now we're saying, okay, there's this phase change process in the boiler where we're going from a saturated liquid to a saturated vapor, but we're going to continue beyond that point. So instead of just stopping where it's a saturated vapor, we're going to superheat that steam until it's a superheated steam, and then we run it through our turbine. So that eliminates the problem of having too much condensation in the turbine, the impingement on the blades, knocking things out of balance, wear and tear on our equipment. And it still allows us to achieve these isothermal processes with phase change. But in this case, we're isothermal from state 2 to 3 for a portion of it, just during the phase change part, and then we begin to superheat. So it's only isothermal for a short portion of the process. Did you have a question, Jajon?
I was going to say, for instance, there's one of the pump steam that you're talking about.
Well, no, this is the compressed liquid region over here, right? So we're outside the dome. This is liquid. Here, we're pumping up just to the boiler pressure, and then we're increasing the temperature of the fluid. So here it's a liquid, then it becomes a liquid vapor mixture as we're evaporating it, and then we continue to superheat. Right, yeah, it's heating up here. So this is the pump compression process. This is the turbine process. This is the boiler. This whole line is the boiler, and then this line is the condenser. Okay, so we can achieve some of the same goals by evaporating and condensing using a boiler and condenser. But now, because we've superheated the steam in the boiler, it's better for power generation within our turbine, and it's more conducive to pumping because we're not trying to pump a liquid vapor mixture. Okay, so we've altered the cycle. This is called the Rankine Vapor power cycle, and it's one that comes up a lot in thermodynamics. There's modifications to this cycle that make it even more efficient that we'll talk about all through. We'll touch on it at the end, and then we'll talk about it in the second semester of thermo as well. Okay, so state 1 to 2 is isentropic compression in a pump. State 2 to 3 is a constant pressure heat addition in the boiler. So previously in the Carnot cycle, it's constant pressure and constant temperature. This is just constant pressure, and the temperature changes. So it is constant for a while, then increases further. 3 to 4 is isentropic expansion in a turbine. And 4 to 1 is this heat rejection process in the condenser, which also happens to be isothermal because we're maintaining that line under the dome for the duration of the process. Okay, so 4 to 1 is isobaric and isothermal, but 2 to 3 is just isobaric or constant pressure. So the assumption here with the Rankine vapor power cycle, if you might notice that from 3 to 4 and 1 to 2 and 3 to 4, they're isentropic processes. Okay, so this is still an idealized cycle. We're still trying to look at a really good case, best case scenario, but still having these positive attributes by modifying the Carnot cycle to fit our needs and our working fluid. Any questions on that? Okay. So this is just further description of what happens in the diagram. We've kind of already talked about this, but basically water enters the pump as a saturated liquid. It's compressed to the boiler pressure. The boiler superheats the liquid. It's run through the turbine. The temperature decreases, and the steam at the end is a hopefully just slightly liquid vapor mixture, mostly vapor. It enters the condenser as a saturated vapor just below that line, and then it's rejected. Heat is rejected from the steam until it becomes a liquid. Then it goes back to the pump. Yes?
What, one says the HX.
Heat exchanger.
Oh.
Heat exchanger, yeah. That's common notation, abbreviation, yeah. Okay. Any other questions? And a boiler is a heat exchanger. A condenser is also a heat exchanger. So heat exchanger doesn't just mean that you're hot. It's just you're exchanging heat in some way or another. Okay. So let's perform an energy analysis of this. So if we use the general form of the energy equation and apply it to each of those devices in the process, we can determine the heat and the work interactions along each phase. And this is these are all devices that we've seen before, so the analysis should be pretty straightforward. In the pump, we're going to assume that it's adiabatic, so the work of the pump is equal to H2 minus H1. And notice this is lowercase, so this is per unit mass, which in chapter 7, we also talked about pump work as being V1 times P2 minus P1. Okay, so either one of those you can use if you know just the specific volume and the pressures, or if you have the enthalpies available to look up. So we have to assume or make the compressed liquid approximation, because although the pump is operating in the compressed liquid region and there is some slight change maybe to the specific volume, we're going to assume that it's incompressible, and we can use the properties of a saturated liquid at state 1. In the boiler, there's no work. However, there is heat into the boiler, and that's equal to H3 minus H2. And the subscripts on these are given in the diagram there. So state 1 is on the saturated liquid line. State 2 is in the compressed liquid region. State 3 is in the superheated region. And state 4 is in the saturated liquid vapor mixture, or hopefully right on that saturated vapor line. So those are the points that we're talking about. The turbine we're going to assume is adiabatic. So Q is equal to 0, and the work of the turbine out is just H3 minus H4. The condenser, again, is not a work-producing or consuming device. It's just a heat transfer device. So Q out of the condenser, meaning we're removing heat from the working fluid in order to condense it, is equal to H4 minus H1. And we can define our thermal efficiency as our desired outcome over our required input, same as we did before. So our desired outcome is a net work out, which is work out minus work in, and that's over Q in from the boiler. So work net out over Q in. And of course, the work net out is going to be the work of the turbine minus the work of the pump. So that's the out from the turbine into the pump. And the pump work should be relatively small, like significantly smaller than the turbine work out, which is another reason why we like to use a pump rather than a compressor, is that it, because the specific volume is so much smaller, it requires less work input than it would if we were trying to compress a vapor instead of a liquid. So let's do some examples on this. I have one that's from the book that's, we'll just go through it step by step to clarify some of the points, and then another one that's a homework style problem that we'll go through as well. Okay, so in this problem, we have a power plant operating on the simple ideal Rankine cycle. Steam enters the turbine at 3 megapascals and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascals. We assume X1 is equal to 0, P2 is equal to P3, which is 3 megapascals, and T3 is 350. So we want to determine the thermal efficiency of this cycle. And what is thermal efficiency for the Rankine cycle? Yeah. So it's the desired out over the required in. So desired out is work net out over Q in. And we're not given a mass flow rate, so it's fairly safe to assume that we're going to be working in lowercase. So it's work of the turbine out minus work of the pump in divided by Q in. And where does Q come into our cycle? In the boiler. Okay. So we need to find the turbine work out, the pump work in, and Q in to our boiler. So let's start looking up properties. Let's first find, let's say, the pump work in. So pump work will occur from state 1 to state 2. So let's look up some properties at state 1 and state 2. And what is the equation for pump work in? From the previous slide. We can use the enthalpies or, yeah, V1 times P2 minus P1. Specific volume. In that case, because it's lowercase w, it would have to be a lowercase v. If it was uppercase w, then it would have to be uppercase v, total volume. Okay, so state 1, we're going to need the pressure and the specific volume. Pressure is given at state 1 is what? Yeah, 75 kilopascals. And V1, how do we find V1? It's a compressed liquid, or a saturated liquid at state 1. Yeah, so at 75 kilopascals, we'll look up the saturation temperature. And then we go to that table, the saturation temperature, we can just look up V sub F. So at 75 kilopascals, state 1, in table A5, our specific volume is 0.001037. Meters cubed per kilogram. Okay, now state 2, we know the pressure is 3 megapascals. Okay, is that all the information that we need to solve for the pump work in? Yeah. Okay, so the work of the pump in is equal to V1 times P2 minus P1, being careful about units, 0.001037 meters cubed per kilogram, multiplied by P2, which is 3 megapascals, but how do we write that in kilopascals? 3,000 kilopascals minus 75 kilopascals. So we calculate the numbers on that, and we get 3.033 kilojoules per kilogram. Okay, so that's the pump work in. We need to find the turbine work out. So turbine occurs between state 3 and state 4, right? What information do we know about state 3? Okay, so the temperature is 350. And what about state 4? What do we know? Okay, so P4 is equal to 75 kilopascals. Do we know anything else about state 4? Another property value? It's not superheated. Okay, so the quality is given at state 1. It's not given at state 2 or at state 4. It's not going to be the same quality because it's going to be closer to the edge of the dome. But what do we know about this turbine? So if we're operating on an ideal Rankine cycle, not the same temperature, that's a TS diagram there. Temperature changes, pressure changes. Isentropic. Okay, isentropic, so that means that if we look up S3, then S4 will be the same. Okay, so at state 3, if we look up S3, it's 6.7450 kilojoules per kilogram Kelvin. So S4 is the same value, which then allows us to find H4 by interpolation. In order to do that, we know H4, if we look at this S3 value at 75 kilopascals, let's see what state we're in. Let's see if we're on the dome, above the dome, under the dome. So at 75 kilopascals with our entropy value as given, are we in between S sub F and S sub G at 75 kilopascals? Yeah, we're in between, which means we need to do what? We need to interpolate. But when we're under the dome, in order to interpolate and find exactly where we are, what's the thing we have to find? The quality. Okay, so H4 is going to be HF plus X, HFG. And X is going to be equal to this S4 minus S sub F over SFG. Okay, so we use this S4 value, which is the same as S3, to find the quality. So SF and SFG just come from the table at 75 kilopascals. It's table A5. And then we plug that back into here using, again, H sub F and HFG. So the numbers we get on that quality is 0.886, which gives us an enthalpy of 2402.75 kilojoules per kilogram. Okay, so we have the enthalpy at state 4. We just need to look up the enthalpy at state 3, which is 3116.1 kilojoules per kilogram. No, because you don't know any H's. You use your entropy to solve for X, and then you use X to figure out your enthalpy. So basically what happens when you're under the dome and you find that your entropy value is here, right? Okay, so you know it's isentropic, your entropy is not going to change from this state, so you find out where you are here on this TS diagram. So you say, okay, my entropy is here, I'm going to figure out what the quality is at that point. And in order to do that, you say, okay, my value is this, S sub F is this, S sub G is this. I take the difference between SF and SG, put that in the denominator, and then I subtract the difference between this and this. So you're taking this difference over this difference to figure out your quality. Once you know the quality, then you can say, okay, I know the quality, now I can figure out where I am on the line for enthalpy. So you have to use the known property value to find the quality, use the quality to find the unknown property value. The same procedure would follow if, let's say, you knew the volume was constant. You use the volume to find the quality, use the quality to find the enthalpy, or whatever it ends up being. So you can do that with entropy, enthalpy, specific volume, internal energy. You can't do it with pressure or temperature because they're not used to find quality. They have no meaning when it comes to quality. Because I already know the temperature and pressure, and it's a superheated vapor. Yeah, so it's the state's fixed there. With this one, I need to find the quality. And this is the part that people have the most trouble with on exams, I've noticed. This step here, having a known property value, using it to find the quality, using that quality to find your unknown property value. So anytime you end up in the liquid vapor region, that's the procedure you need to follow if it's not already fixed. Like if quality is not given in the problem or something like that. Okay, we're going to move along. So our turbine work is equal to this H3 minus H4. So if we plug in the numbers for that, H3 is 3116.1. H4 is 2402.75 kilojoules per kilogram. Then we get a value of, I didn't calculate it directly because I did these two in one step, so some number. Yes. 713.35. Okay, kilojoules per kilogram. Thank you, Dejan. Okay, so then we find our work net out is equal to this value minus this value. So that gives us 710.3 kilojoules per kilogram. So we found this. Well, we found this because we don't know the mass. Okay, so now we need to find Q in. Where is Q in? What's okay, from state 2 to state 3. So we have all the property values at state 3. That's good. We already have an enthalpy. How do we find the enthalpy at state 2? What do we know about state 2? We know the pressure. Do we know anything else? It's also an isentropic process. So if we look up S1, it's equal to 1.2132 kilojoules per kilogram Kelvin. S2 is equal to S1. Okay, so state 1 to state 2 is an isentropic process. But this still doesn't necessarily help us because we're in the compressed liquid region. We don't have very good tables for that. However, we know that the pump work is equal to V1 times P2 minus P1. It's also equal to H2 minus H1. We know H1, right? We can look it up easily. H1 is just H sub F at this temperature. So H1 is 384.44 kilojoules per kilogram. So then we can solve for H2 because we already calculated the pump work. And if we do that, the value that we get is going to be equal to, H2 is equal to H1 plus the work of the pump in. And that's 384.44 plus the 3.033 is 387.47 kilojoules per kilogram. Okay. So now we know H2, we know H3. We can calculate our boiler work, Q in, is equal to H3 minus H2. So that's 3116.1 minus 387.47 kilojoules per kilogram is 2728.63 kilojoules per kilogram. We know our work net out. We know Q in. So our thermal efficiency is equal to 710.3 divided by 2728.63 kilojoules per kilogram in both. Our thermal efficiency is 26%. Woohoo! So that's the thermal efficiency for the entire cycle, not any one component. It's a big involved process to figure that out, right? Okay, but what's that? That's a normal percentage. Yeah. And this is an idealized cycle. Yeah. So you can see how inefficient it is to try to convert heat into work. And let's not even talk about all the entropy generated during that process. Okay, so these are the strategies and the tips that you need to use. So if you're analyzing an idealized cycle, knowing that between state 3 and 4 is isentropic, so you can find your other property values, figuring out how to calculate the quality at state 4, and then from state 1 to state 2, also isentropic, and then using the calculated pump work to solve for that second enthalpy. Because you can't look it up directly. We don't have compressed liquid tables, and we don't know the temperature, so solving for the enthalpy that way. If it's an ideal Rankine cycle. Yeah. We will do some where it's a not ideal Rankine cycle, in which case you have to find state 4S and state 4 actual. So these problems can get very involved, where one problem will take you like 3 pages. Well, so it kind of does like that. Yes. Yeah. Not always. Yeah, so knowing what it looks like and how to analyze it, and then remembering, you know, the different steps and the components and pieces of the process. It may just be a word problem that says simple ideal Rankine cycle. Then you'd have to be like, okay, what's in the Rankine cycle? All right, boiler, turbine, condenser, pump. And remembering that and what it looks like. But if it is an ideal Rankine cycle, then you know too that it's isentropic pump and an isentropic turbine. Okay, any other questions on that? So let's do another example. We'll try to move through this one a little bit quicker since we already kind of know how to do it, hopefully. Okay, so steam power plant operates on the simple ideal Rankine cycle, has a net power output of 45 megawatts. Steam enters the turbine at 7 megapascals and 500 Celsius, and it's cooled to the condenser at a pressure of 10 kilopascals by running cooling water from a lake, blah, 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 blah. Show the cycle on a TS diagram with respect to saturation lines and determine the thermal efficiency of the cycle, the mass flow rate of the steam, and the temperature rise of the cooling water. Okay, so there's a few more steps to this one. We know how to find the thermal efficiency. We can go through that fairly easily. The brunt of these problems is fixing all the states and finding the property values. Okay, that's the biggest part of the work that you will do. Everything else is just plugging stuff into equations. Finding the properties is what is can be the trickier part. So what does it look like on a TS diagram with respect to saturation lines? Does somebody want to try to draw it? Jordan? You made eye contact. We'll help you. So you can draw it in your books too and guess and then see if you get the same thing. It's good practice to try to remember what was just on the previous slide, right? It's a different temperatures, different pressures, but the graph will look the same. Okay, probably this line would be lower down, so it would maybe be more like that. This would go higher, but he did very well. No. You have the general gist of what happens. So that's what happens in the diagram. Okay, so we're going to start labeling states. State 1, looking up property values. State 2, state 3, state 4. Okay, right now state 3 is well defined. We can look up all the property values at state 3. It's a superheated vapor. So P3 is 7,000 kilopascals. T3 is 500 degrees Celsius. We'll look up H3 is 3411.4 kilojoules per kilogram. And S3 is 6.8000 kilojoules per kilogram Kelvin. So we can look up everything at state 3. That's kind of nice. State 1, we similarly can look up all of our properties. So H1 is 191.81 kilojoules per kilogram. V1 is 0.001010 meters cubed per kilogram. S1 is 0.6492 kilojoules per kilogram Kelvin. And this is at what pressure? 10 kilopascals. Okay, so state 1 and state 3 are well defined. How do we figure out what's going on at state 2 and state 4? Okay, so state 2, we know that S1 is equal to S2, or S2 is equal to S1. We know our pressure at state 2 is going to be the same pressure as state 3, so P2 is 7,000 kilopascals. How do we find H2? Okay, so when we find the pump work, we're going to find H2 is equal to H1 plus the work of the pump. Okay, we don't know that yet. You had the right equation. We haven't gotten there yet. Okay, what about state 4? What do we know about state 4? Also isentropic. So S4 is equal to S3. How do we find where we are under the dome? We need to figure out the quality. How do we do that? Using S. So X is equal to S4 minus S sub F over SFG. So this is property values where P is equal to 10 kilopascals, right? So from that table, and then H4 is equal to H sub F plus X HFG. X is equal to 0. Yeah. So it starts out as a saturated liquid. Because you compress it up to the boiler pressure. And this is a line, this follows a line of constant pressure. So that process is a constant pressure process. So and this is the idealized cycle. In the actual cycle, other stuff happens, but in the idealized cycle, it follows that constant pressure line. Yep. Okay. Any other questions on that? So we can fix all of our states. We just need to go through the work to do it. So first part, we're trying to find thermal efficiency. So we need to, again, calculate the work net out over Q in, which is equal to the work of the turbine minus work of the pump over Q in. Well, so for thermal efficiency, if we put in the mass flow rate, then it doesn't matter. But yeah, so we could. But it just cancels itself out in this case. Okay, so the work of the turbine is what? Yeah, it's H3 minus H4 minus the work of the pump. And what's the work of the pump? Yes, but this is lowercase. So we could, let's see. Yeah, so we're going to do it this way, but we use that later to find the mass flow rate. We don't know the mass flow rate. We do know that of the steam in the boiler. We know the mass flow rate of the cooling water. So we haven't gotten there yet. Okay, so H3 minus H4, how do we find the pump work? So it's V1 times P2 minus P1. And then Q in, what's Q in? H3 minus H2. Okay, so we have all of those property values. We put them in. For sake of time, I'm not going to write that all out. We find that our thermal efficiency is equal to 38.9%. So a little more efficient than our previous example. Okay, so that's part A. Now the mass flow rate of the steam, m dot of the steam. So we have a net power output of 45 megawatts. And cooling water is coming into the condenser at a rate of 2,000 kilograms per second. We don't even ever use that. That's funny. So we don't need to know that. Okay, so work dot net out is going to be equal to m dot times the work out net, work net out, right? So we can solve for m dot of the steam is equal to work dot net out over this work out term. Okay, so the work out term is this again. The work net out is 45,000 kilowatts divided by H3 minus H4 minus the V1, P2 minus P1. So little w times mass is equal to big W. Little w times m dot is equal to w dot. So little w is work per unit mass. Little h is enthalpy per unit mass. Little u is internal energy per unit mass. It's always divided through by the mass when it's lowercase. That's the nomenclature that we use. Okay, so we find m dot of the steam is equal to 35.97 kilograms per second. And then part C, the temperature rise of the cooling water. So we want to figure out how much heat is added to the cooling water and how that temperature increases, which I will do, actually, I'll just erase this part. Okay, so where is the cooling water? Where is it interacting with our steam? In the condenser. Okay, so it's a heat exchanger. So we can imagine maybe our condenser looks something like this, where we have, let's say, maybe cooling water coming in, and then our steam enters here, condenses, and then is drained out the bottom. Okay, so the cooling water is maybe like pipes running through this condenser. As the steam hits those pipes, it reduces the temperature of the steam, adds a little bit of heat to the cooling water, and then as the cooling water exits, it's slightly higher than it was when it went through, and the steam is condensed, so it's drained off the bottom of the condenser. Does that make sense? Yes? No? Okay. So it's coming out here, going in here, going out there. Okay, so we know a mass flow rate of the cooling water. We've calculated the mass flow rate of the steam. We want to determine how much heat is being exchanged in the condenser. So we need to figure out this Q out term. And how do we find Q out of condenser? What is it? So this heat being removed here. Okay, so H4 minus H1. So we put in the numbers for that. Oh, I never did solve for X and H over here. I'll put those down so you have them. So X is equal to 0.820. And H4 is 2153.33 kilojoules per kilogram. Okay. I'm going through this kind of fast because it's similar to what we've already done, but I want to get to some other examples and stuff we have to talk about. Okay, so Q out is equal to H4 minus H1 within the condenser, right? So we also have cooling water. We know the mass flow rate of the cooling water. So Q in to the cooling water, this is different than the Q in to the boiler, is going to be equal to C sub P times T2 minus, well, no. I'm not going to use 2 and 1 because that's confusing. Temperature out minus temperature in of the cooling water. Okay, so then we can also say that Q dot out is equal to M dot times H4 minus H1, and Q dot in is equal to M dot of the cooling water, C sub P times T out minus T in. Okay, so we set these two equal to one another and solve for T out minus T in. So we find that the delta T of the cooling water, so we want to know how much the temperature increases, so it's T out minus T in, is equal to the mass flow rate of the water through the steam through the cycle times H4 minus H1 divided by the mass flow rate of the cooling water, C sub P of the cooling water. And we can just use C sub P of water at ambient conditions, which is 4.18 kilojoules per kilogram Kelvin. So if we plug in the numbers for that, we have it right here. Yep. So we plug in all the numbers for that and we find it's 8.4 degrees Celsius. So I'll leave that to you if you want to test those numbers, put those in, make sure you fully understand it so we can move on. Because these problems do kind of take a long time as we're explaining and asking. Okay. Heat rate. This is a common term used to denote the energy conversion efficiency of power plants. So we've talked about it previously a little bit just in some of the problems. And so it's the amount of heat supplied in BTUs that is converted to electricity in kilowatt hours. And this is the only time when you're really concerned about what your heat supply is. So if you need to calculate the heat rate and determine maybe how expensive it is to operate under these conditions or something like that. So the thermal efficiency and the heat rate are related just through the unit conversion between BTUs and kilowatts per hour. So let's talk about now, we've looked at the ideal Rankine cycle. In reality, our pump is not isentropic and our turbine is not isentropic and we have head losses within our pipes. So there's certain things that cause the actual vapor power cycle to be slightly different from an idealized one. So friction, heat loss, deviation from isentropic behavior, and then any other considerations that might be like the pipe has a crack in it and there's steam leaking out. Or maybe there's auxiliary equipment that's that's being used to measure things within the power plant. Or there's cavitation in the pump, or there's impingement in the turbine. All of these can serve to reduce the efficiency of each of those individual devices and then serve to kind of change the behavior of the actual Rankine cycle. So you can see how the deviation from ideal behavior occurs, that really maybe there's a pressure drop in the boiler that causes us to not follow exactly that constant pressure line, or the irreversibilities in the turbine, or some of these other factors that come into play. So instead of following a perfectly isentropic course, we're actually ending up somewhere over here where we're at a higher entropy state after coming out of the turbine and after coming out of the pump. So then, if we're looking at this deviation, we can calculate or use the isentropic efficiencies that we talked about in Chapter 7 to determine maybe what our actual enthalpy will be. So if we know, the idealized state, so state 1, 2, 3, and 4 in the isentropic case, and then we're given maybe the isentropic efficiency of our pump or our turbine, we can calculate the actual enthalpy using these relations here. So instead of having 4 states, it's like you have 6 states, and it's really fun. So let's do an example of that, because this one will require a little bit more. But it's the same stuff we've been doing. There's just an additional state to consider. And we use the information from state 4 to calculate state 4 actual. We use the information at state 2 to find state 2 actual. So if we look at the thermal efficiency of our idealized cycle versus the thermal efficiency of our actual cycle, in some cases, we would find our actual thermal efficiency is lower, right? Or that our actual turbine workout is slightly reduced. Okay, so a steam power plant operates on the cycle shown above if the isentropic efficiency of the turbine is 87% and the efficiency of the pump is 85%. Determine the thermal efficiency of the cycle, the net power output with a flow rate of 15 kilograms per second, and that's it. Only have to find 2 things. That's good. And those are 2 pretty easy things to find. So what we have to do and what we have to be careful about is making sure that we keep close track of all of our states and don't mix things up. Okay, so we have state 1, 2, 3, 4, 5, 6. Right, okay. State 1, state 2, state 3, 4, 5, and state 6. Okay, so state 6, we're going to calculate it first as isentropic, and then we're going to use those values to find actual conditions. The same goes for state 2, that we're looking at it as if it were isentropic first, and then we use the isentropic efficiency to find our actual values. Okay. So state 1, we find specific volume is 0.001007 meters cubed per kilogram, and S1 is 0.5455 kilojoules per kilogram Kelvin. At state 2, S2 is equal to S1, and H2 isentropic is going to be equal to H1 plus the work of the pump in, the isentropic work of the pump in. State 3, we can find the enthalpy pretty easily because we're given a pressure and temperature. So H3, based on the temperature of 35 degrees Celsius and 15.9 megapascals, we can interpolate on the table to find it's 160.8 kilojoules per kilogram. State 4 is also well defined. It's 15.2 megapascals, so there's a pressure drop in the boiler in 625 degrees C. So H4 is 3645 kilojoules per kilogram. State 5 is 15 megapascals, 600 degrees C. So again, well defined. So we find H5 is 3581 kilojoules per kilogram. And then S5 is 6.677 kilojoules per kilogram Kelvin. State 6 is 10 kilopascals. So we can find that S6 is equal to S5 H6S will be equal to 2114 kilojoules per kilogram. I'll just give you that. Okay, so thermal efficiency is going to be equal to the turbine work out minus the pump work in over Q in. Okay, so the turbine, let's see, determine the thermal efficiency of the cycle. So we could calculate a thermal efficiency of the idealized cycle, how we did previously, but we want to know the actual thermal efficiency of this entire cycle. Okay. The isentropic efficiency of the turbine is equal to H3 minus H4A over H3 minus H4S. So we use this, we know H3, to solve for H4 actual is equal to the turbine efficiency times H3 minus H4S minus H3. So negative H4A is equal to that. H4A with a turbine efficiency of 87%, we find that H4A, I didn't even actually solve for it. Okay, I did it a different way. I solved for the work of the turbine isentropic is equal to H3 minus H4S. Oh, no. Sorry, guys. The numbers are different. I gotta look at this instead. Okay, so the work of the turbine, starting over, erase all that, scratch it out. The work of the turbine isentropic is state 6, or state 5 to state 6S. So it's H5 minus H6S. I should just follow my notes instead of trying to do it. Okay. So this 3581 minus 2114 kilojoules per kilogram. So the isentropic turbine work is 1467 kilojoules per kilogram. The actual turbine work is going to be this isentropic turbine work multiplied by the efficiency. So that value we get is 1276.29 kilojoules per kilogram. So you do the same thing for the pump work, that the work of the pump isentropic is equal to V1 times P2 S minus P1. So that value is 16.1 kilojoules per kilogram. The work of the pump actual is equal to the work of the pump isentropic divided by the pump efficiency, or the isentropic pump efficiency. So we get it's 18.95 kilojoules per kilogram.
What's that?
1276.29, yeah. Okay, so we have now the turbine actual, pump actual. We need to find Q in to the boiler. So Q in is equal just to H4 minus H3 in this case. H4 minus H3, so that's just right on either side of the boiler. It's confusing because it's different subscripts than we used previously. So this is 3484.2 kilojoules per kilogram. So our thermal efficiency for our actual cycle is going to be the work of the turbine, 1467. The actual work of the turbine, which is 1276.2 minus the actual work of the pump, which is 18.95 kilojoules per kilogram, divided by Q in, which is this 3484.2 kilojoules per kilogram. So our actual thermal efficiency is 36.1%. We could also calculate the isentropic thermal efficiency if it were isentropic using this value and this value, but we're not doing it that way. So then the net power output is going to be this work of the turbine out minus the work of the pump in, multiplied by the mass flow rate of 15 kilograms per second. So that's 15 kilograms per second multiplied by 1276.29 minus 16.1, minus 18.95, which is equal to 18.9 megawatts. Okay, so the problems are kind of involved, right? Okay, so how can we increase the efficiency? Because even small increases in thermal efficiency can mean a pretty significant savings when we're doing it on a huge scale, so monetary savings. So in general, as before, by increasing the temperature of the boiler or decreasing the temperature of the condenser can increase the efficiency. So we can do this by lowering the condenser pressure, which will lower our T-sub-L. We can superheat the steam to an even higher temperature, and we can increase the boiler pressure. So there are constraints on how far we can do that, and certain advantages and disadvantages. So lowering condenser pressure serves to increase the thermal efficiency. However, as we lower that line, we're moving further and further into the liquid vapor region. So 0.4, as it gets lower and lower, it's by nature just moving further from that saturated vapor line. So that's not good for the turbine. And if we have our pressure subatmospheric, so if we decrease it so much that it's subatmospheric, then air leaking into the pump or into the condenser can occur, which is not desirable, and it can cause, of course, problems with the turbine at that final state. Superheating the steam is constrained by material constraints of our boiler, so we can't superheat it above the temperature of warping or destroying the metal that we're using or whatever material it is we're using. So that's a limit there. It also, we have to factor in how much does it cost to increase the temperature. So are we consuming more fuel in order to do that, which overcomes any savings that we account for in our efficiency. So there's a balance there, an optimization process in order to do that. And increasing the boiler pressure automatically increases T sub H, but it can cause additional moisture in the turbine. And high boiler pressure can lead to catastrophic failure of this power plant, which is completely undesirable, both from a safety standpoint, but then also having to take the power plant offline in order to make repairs to it is extremely costly. That they never like to have to do that. That's a bad thing. So we can rework it and rethink it. And these are mostly just kind of FYI things, that there's a couple of different things you can do. Similar to when we were trying to reduce the compressor input, we can have a two-stage turbine now, so where we reheat the fluid in the middle of it. If you remember from the compressor example, we were cooling the fluid in between. Well, with the turbine, we heat it up in between, which allows us to kind of still operate at a higher temperature in the boiler, increases our thermal efficiency, but negates some of the possible negative side effects from just heating it all in one go before it goes into the turbine itself. And then there's also the regenerative Rankine cycle, where coming out of the condenser, we pump our some of the steam from the turbine into this feed water heater, which sort of serves to increase the temperature of our condensate prior to going to the boiler. So it's like a way of using some of the heat from the steam in the turbine to preheat what's coming out of the condenser. There's somewhat of a cost savings there by doing it that way. That's called the regenerative Rankine cycle. And then we can combine those two together with a much more complicated cycle where we reheat and we regenerate. And despite the complications, it may end up being a more cost-effective way to run our power plant by putting in these additional stages and adding equipment. So that's an optimization design process that you have to figure out. So there's a lecture for today. Thank you for your patience.